Welcome back. So in this video, we are going to finish off this topic and we would see how would you compute the water level gamma naught and how would you compute the capacity for a given distribution of the channel. So we have been discussing this problem for the last two videos where we want to minimize this problem because this B log base 2 of 1 plus Pj gamma over P bar times Pj tilde is nothing but the capacity that you would get under this regime. Where again, for the reference, what we are talking about is that we want to compute the capacity where both the transmitter and the receiver have the channel side information, and in this case because the transmitter has the channel side information, we can do the power control. So these PJs are the transmitted power when the channel is in the state J, and because that was a maximizing function to write in order to write this into a standard form, we have multiplied this with a negative sign so that we can write this problem, which is our objective function, and then we have a total average power constraint, that is the total average power must be less than or equals to P bar, and we have brought P bar here so that we can bring this constraint as well in the standard form. So in the last video, we solved this problem using the method of Lagrangian, and we proved that the power control that we would get by solving through the method of Lagrangian is that Pj over P bar is nothing but 1 over gamma naught minus 1 over gamma, and we put a plus here to make note that this power level would only be possible if this quantity is positive. If 1 over gamma naught minus 1 over gamma is negative, then you would not put any power in the channel. So we said that this concept can be thought of as a water filling solution. So we plotted 1 over gamma with respect to gamma on this axis. So if we have a discrete time channel, as gamma increases, 1 over gamma would decrease. So you have this kind of a decreasing function. And then this 1 over gamma curve can be thought of as a base of the container. And then you have a fixed water level, which is 1 over gamma naught. So you need to put in water. By water, we mean the power we are going to put in till the time we reach this 1 over gamma naught, which is your water level. So hence 1 over gamma naught minus 1 over gamma, by the way, this is 1 over gamma, would give you the total power allocated when the channel is in the jth state. And if your channel is so bad that 1 over gamma is greater than 1 over gamma naught, then you would not put any power in the channel at all. So now we would try to compute what is how to compute 1 over gamma naught. So remember, Pj over P bar is 1 over gamma naught minus 1 over gamma plus. So if we put this back into our equation of the capacity, remember C is what? Summation j equals 1 to capital N B log base 2 of 1 plus Pj gamma over P bar times Pj tilde. Now we know what is Pj over P bar. So that would be equals to summation j equals 1 to capital N B log base 2 of 1 plus 1 over gamma naught minus 1 over gamma times gamma Pj tilde. That would be equals to summation j equals 1 to capital N B log base 2 of 1 plus gamma over gamma naught minus gamma over gamma, which would be equals to 1. So that 1 would cancel out with this one, and we are left with gamma over gamma naught times Pj tilde. So that is our equation for the capacity with this water filling solution. We still have to figure out how would you compute this gamma naught, right? So that we're going to do next. So this 1 over gamma naught or gamma naught would be computed using the power constraint. Remember, we know that the, the maximum between 0 and 1 over gamma naught minus 1 over gamma is our um, power allocation strategy. That means if 0 is greater than this quantity, we would allocate 0 power into the channel. So that is our Pj over P naught, P bar. Remember, we put a plus on 1 over gamma, not 1 over gamma. Uh, Another way of writing the same thing is that your Pj over P bar or your power allocation strategy would be maximum of 0, comma 1 over gamma naught minus 1 over gamma. So that is a constraint we have to follow. So now that would mean that summation j equals 1 to capital N pj tilde minus p bar must be less than or equals to 0, or you can change that inequality to a equality. So that is a power constraint that we must adhere to. And this is a power constraint that can help us in computing the water level gamma naught. So I would solve this with the help of an example. Remember, this is a water filling solution is a unique solution, and this is one of the only solutions where you can get sometimes in a very rare scenarios a capacity which is even greater than the capacity of AWGN channel. And one of the examples that we are going to do is going to demonstrate exactly that. Okay, so let's do an example. Suppose you are given a three-state channel. Suppose gamma 1 is equals to 0.01, gamma 2 is equals to 0.05, and gamma 3 is equals to 0.1. So you can see that the signal to noise ratios are really low for all three states. So and the respective probabilities with which these are going to happen is P1 tilde is equals to zero point 0.1, P2 tilde is equals to 0.5, and P3 tilde is equals to zero point 0.4. Of course, summation Pi tilde I from 1 to 3 must be equals to 1, and that is the case. Also, you are given that the bandwidth is 30 kilohertz, and that's it. And you are required to find out the power allocation strategy and the respective capacity if both Tx and Rx have CSI. So find capacity with Tx, Rx, CSI with power control. That is what we're going to find out. The first thing we need to do is to compute uh, gamma naught, or which channel states can we use. Remember, okay. So let's try to first compute the capacity with AWGN channel. So capacity with AWGN. That means you need to first compute what is the um, average signal to noise ratio. So now we need to compute what is gamma bar. So gamma bar is what? Summation I equals 1 to 3 gamma I 1 over 3, and that would give us the average signal to noise ratio. So the average signal to noise ratio, if we plug in these values, turns out to be excuse me for my error. So the average signal to noise ratio, if you want to compute for this, would be summation I equals 1 to 3 gamma I times Pi tilde, which is the probability with which this gamma is going to happen. So that would be equals to 0.01 times zero point 0.1 plus 0.05 times 0.5 plus 0.1 times zero point 0.4. So that turns out to be 0.066. So that is the capacity. That is the average signal to noise ratio for these conditions, right? Remember, you're given these conditions, and if you compute gamma bar under these conditions, this turns out to be your average signal to noise ratio. Now we have this average signal to noise ratio. We can compute what is the capacity of the AWGN channel under this average SNR. So CAWGN would be simply B log base 2 of 1 plus gamma bar. That would turn out to be 30 into 10 plus 3 log base 2 of 1 plus 0.066 bits per second. And that turns out to be 2.76 kilobits per second, 766 kilobits per second. So what we're doing in this example is to compare the three strategies we have learned so far. So this is the capacity under AWGN. Then in the next part, we are going to compute what is the capacity when only the receiver has the channel side information, or both receiver and transmitter have the channel side information, but the transmitter is not doing the power control. So that is the second part. Let's try to find that out in the second part. So now let's compute what would be the capacity under these conditions when capacity with Rx CSI only. So when only the receiver has the channel side information, the capacity C is given by the ergodic capacity. So C would be equals to summation I equals 1 to 3 B log base 2 of 1 plus gamma I Pi tilde. And if you compute that, if you plug in the values of gamma I and B equals to 30 kilohertz, it turns out to be 2.748 kilobits per second. And you can see that this ergodic capacity, is slightly lesser than the capacity we computed for AWGN channel. So that we proved through the Jensen's inequality as well, that the ergodic capacity would always be less than or equals to the capacity under AWGN. And now we would compute what would be the capacity with under the optimal power control. So the part 3. Remember, this would always also be the capacity with TX, RX, CSI, but with only rate control and no power control. So the capacity would be the same under those conditions. Now the third part is the capacity with optimal power control. Right? So now we need to compute what is the capacity with optimal power control. We know that what is the power constraint? Summation I equals 1 to 3 Pi times Pi tilde is equals to P bar is your power control, or you can also write it as summation I equals 1 to 3 Pi over P bar times Pi tilde is equals to 1. Okay, so you have brought this P bar on this side. Now Pi over Pi bar, we know in the optimal power control is nothing but 1 over gamma naught minus 1 over gamma. So you can rewrite this power constraint as summation I equals 1 to 3 1 over gamma naught minus 1 over gamma times Pi tilde, and that is equals to 1. Okay, So now um, um, you have everything with you. So remember, this is 1 over gamma means this is you're talking about the channel state you are in. So you can plug in different values of gamma I. So this essentially would be gamma I rather than 1 over gamma. That's the channel state you are in. So let's plug in different values to find out whether this power control works for all three channel states or we have to do something else. So one thing that I want you to understand upfront is that we want that 1 over gamma naught minus 1 over gamma I for all values of I, that must be greater than 0, because otherwise you would have a 0 as your power control. You would pour in no power at all. What does this mean? This means that 1 over gamma naught must be greater than 1 over gamma I. In other words, your gamma naught, if you flip this around, gamma naught must be less than your gamma I. So whatever gamma naught you compute under this using this law, this gamma naught should be less than all gamma i's that you have used to compute that gamma naught. Otherwise, that doesn't work. And then you have to reduce the states that you are using. So let's go ahead with the three states that we are using and see whether this works or not. So first, let's use all three states. So if you use all three states, that would mean that 1 over gamma naught minus 1 over zero point zero 0.01 times the probability, which is zero point 0.1, plus 1 over gamma naught minus 1 over zero point zero 0.05 times the probability zero point 0.5 plus 1 over gamma naught minus 1 over zero point 0.1 times the probability of zero point 0.4, that must be equals to 1. So if that is the case, and we compute gamma naught with this, so gamma naught turns out to be 0.04. Now this 0.04 is greater than 0.01, which is the minimum value of the gamma j or gamma I you had. So, so that means this rule doesn't work if we use all three values of gamma naught. Remember, we said that gamma naught must be less than gamma I for all values of I that is used in this expression. So what would you do next? The logical step would be that we would not make use of this state, which is the lowest state. So if we don't use this state, we would only use the states I equals to 2 and I equals to 3. That means now let's try to compute a gamma naught. Summation j equals 2 to 3, 1 over gamma naught minus 1 over gamma j times pj tilde is equals to 1. And if you now plug in last two values of the states, that means 1 over gamma naught minus 1 over 0.05 times 0.5 plus 1 over gamma naught minus 1 over zero point 0.1 times zero point 0.4 equals to 1. If you plug in these values and compute what is gamma naught, so gamma naught turns out to be 0.06. So it is still greater than 0.05, which is the first state you used in this. That means this again would not give you the optimal performance. So the last step is to use only one state, which is zero point 0.1. So let's see what it happens. So now if we use only the one state, let's see, 1 over gamma naught minus 1 over zero point 0.1 times zero point 0.4 must be equals to 1. And now if we compute gamma naught with this, gamma naught turns out to be 0.08, which by the way is less than zero point 0.1. So now this would work. So now this gamma naught is less than zero point 0.1, which is your state, zero point 0.1. So that means that your optimal, you would get an optimal capacity when you would not transmit anything when you are in the state 0.01. You would not transmit anything when you're in the state 0.05. You only transmit when you are uh, when you are in when the channel in the state with a signal to noise ratio of zero point 0.1. And remember, because both the transmitter and the receiver has a channel side information, you can adapt with these conditions. So now let's see what would be the capacity. So now we have computed gamma naught. Once we have the gamma naught, we can make use of the expression of the capacity um, computed just computed a little earlier to compute what is the capacity of the capacity under this regime. So now all we need to do is to find out what the capacity. So remember, capacity is summation j equals 1 to n b log base 2 of gamma over gamma naught times pj tilde. But in this case, we have used only one state, so your capacity would be equals to b log base 2 of gamma 3 over gamma naught times p3 tilde. And if you plug in the values, that would be would be 30 kilohertz log base 2 of gamma 3, which was zero point 0.1 divided by 0.08 times P3 tilde, which was zero point 0.4. And if we compute the capacity under this condition, that turns out to be 3.862 kilobits per second. So now what you can see already is that the capacity with the optimal power control under this condition where you are always in the low SNR regime is, let me call this capacity with a water filling or under optimal power control. So the capacity with water filling is greater than the capacity under AWGN channel. But that would not happen always, of course. That happens rarely, and and if you are sitting in a condition where you have low SNR, and once in a blue moon you would have a high SNR, and you pour in all your power in that particular state, then under those conditions, under the low SNR regime, your capacity with the water filling solution can be greater than the capacity with AWGN. So with that, we would close this topic of the capacity with transmitter and the receiver channel side information. In the next video, we would talk about the suboptimal, uh, the capacity under the suboptimal conditions. Thank you for your attention.